We are the Sooner Rover team. We are made up of 20 students from a variety of disciplines at the University of Oklahoma. We are excited to show you our best rover yet.
The rover communicates with mission control over a 2.4 GHz antenna capable of transmitting over a kilometer through obstructions. Using custom video streaming and control programs, the operator can finally control the rover without any line of sight. All missions in this video except for autonomous were completed without looking at the rover. Here the rover types out SORO using an Allen wrench that it previously picked up off the ground.
For the fine manipulation tasks, the Sooner rover arm utilizes a wrist capable of pitch and roll via 2 radially mounted motors, and grasping tools through servos. This allows for the fine adjustments required for tasks such as typing and flipping switches. The entire arm is mounted on a belt-driven rotating base that allows for 360-degree reach and repositioning without driving the rover.
Each wheel contains its own embed microcontroller and other protective circuits for the wheel motor. Each embed is connected to a CAN transceiver that allows us to send and receive messages to a singular embed in the electronics box. This approach allows us to mitigate noise from the motors much more effectively than previous years' designs.
Our unique Marzicod design lowers the center of gravity of the rover as the conical volume allows each wheel to house its own motors and electronics. Fins on each conical wheel add traction and grip on steep surfaces. Each axle can rotate independently, meaning that the rover can easily scale large obstacles and difficult terrain without high centering. The independent axle rotation also allows each wheel to maintain nearly constant contact with the ground. This, coupled with the large wheels, enables faster traversal speed than traditional rocker bogie designs. A linear actuator provides extension forward and up, and, combined with hooks mounted on the forearm, provides the bulk of the arm's strength and lifting power as required for aspects of extreme traversal. The mix of strength at the hooks and minute articulation at the wrist allows one arm to complete a variety of URC missions.
The science package consists of a drill and vacuum system with the samples loosened from soil or regolith via drill and placed via vacuum in tubes preloaded with hydrogen peroxide to test for the presence of organics. A positive test is indicated by effervescence of the suspension of liquid sample. Sample 1 was obtained from a molehill and was positive for organics, as is seen in the image on the lower left. Sample 2 was obtained from yard sediments where insects were observed and was also positive, as seen in the lower left image. A sample of beach sand was observed to be negative for organics. Rock samples were analyzed via camera. Samples on the right indicated no life, as seen in sandstone and mudstone. Samples on the left indicated extinct life, including petrified wood and fossils, including trilobites and stromatolites.
We start the autonomous mission by sending the rover a list of latitude and longitudinal coordinates that lead to the desired location for the rover to drive along. It uses GNSS to calculate its current heading and distance from each GPS coordinate. PID is used to control the wheel speeds to ensure that it's driving with the correct heading. For the first 3 legs, once the rover determines it is within 3 meters of the final set of given coordinates for that leg, it stops and turns its LEDs green. We then give it another list of coordinates that lead to the next set point and restart the process. For legs 4 through 6, while the rover is driving through the set of GPS coordinates, it is looking for an AR tag using a RUCO in the YOLO object detection algorithm. If it sees an AR tag, the rover stops, aligns itself with the center of the tag, and then tracks it down using PID until it detects it as within 3 meters of it. Our cameras can see tags from up to 12 meters away. To ensure that we can find tags that are 20 meters away from the given GPS coordinates, we give the rover several sets of coordinates around the given set point so it can drive along them while looking for the tag. This creates an effective search algorithm that can find AR tags from any distance away. For the final leg, the rover looks for 2 AR tags and, once it sees them, aligns itself to their center and determines how far away they are. The rover then drives the calculated distance plus an additional 3 meters to score. Here, the rover completed the full autonomous course. Thank you. We are excited to compete at the 2022 URC.